Teuton Cosmonaut Productions presents Mathematical Mysteries of the Pyramids. The search for truth brings us to the pyramids. Hey, Russell, what are you reading?
Peoples and Places of the Past by National Geographic Society.
And what are you learning?
The Great Pyramid of Cheops is amazing. If you surround it with a three-dimensional rectangle, the volume of the rectangle is exactly 3 times the volume of the pyramid itself. I wonder, were Egypt's ancient architects paying honor to the mystical number 3?
Actually, the ratio of 3 to 1 applies to every pyramid on Earth. Let's investigate. Here are a pyramid and a three-dimensional rectangle with the same base and the same height. Let's see how many pyramids it takes to fill the rectangle. That's 1. That's 2. That's 3.
I can understand why the area of the triangle is 1/2 times the base times the height. But I don't understand why this is 3 times as big as this. Do you have to be a genius to understand?
Maybe this will help. Here's a cube, and the cube can unfold into 6 pyramids. Now here's the same cube we were just looking at after you unfold it a little bit. If all of the sides of the base are equal to 1, I think you can see that the height of the pyramid is 1/2. Now that cube had 6 equal pyramids inside it. And so the volume of the cube, or the volume of each pyramid, is equal to 1/6 the volume of the cube. Let's say that the volume of the whole cube is equal to 1, and the volume of each pyramid is equal to 1/6. Now the volume of each pyramid is also equal to the base of the pyramid times the height of the pyramid times the mystery multiplier n. The base of the pyramid is 1 by 1 equals 1. The height of the pyramid we just saw is equal to 1/2, and then we got the mystery multiplier n. So the volume of each pyramid, when you do the multiplication, equals n over 2. So we know that 1/6 is equal to n over 2. By cross multiplying, we know that 6 times n equals 1 times 2. That's what we have here. We then divide each side of the equation by 6. And on the left side, the 6's cancel, and we are left simply with n. And on the right side, we have 2 over 6, which reduces to 1/3. So we have our magic multiplier. The volume of the pyramid is equal to the base times the height times 1/3.
Okay, I'm convinced that the multiplier is 1/3, but why does the universe work that way?
Why does the universe work like that? Well, to get the answer, let's go back again to the ancient pyramids of Egypt. What we see here is the Great Pyramids of Cheops, which was built around 2560 BC. You'll see that the sides of this pyramid are smooth, or at least they were smooth when the pyramid was originally built. You could slide from the top of the pyramid to the bottom without bouncing. Now here's another ancient pyramid from Egypt. This is the step pyramid Saqqara, which was built around 2600 BC, so it's a little bit older than the Great Pyramid of Cheops. Now the step pyramid has a different kind of structure. You'll see that it's not smooth on the sides, and you could not slide without bouncing from the top to the bottom. You would bounce quite a bit if you took that slide, because the step pyramid is constructed in layers. Okay, here we have two model pyramids, which might make you think of the Great Pyramid of Cheops and that other pyramid from ancient Egypt. This pyramid is a regular pyramid. It has smooth sides. Here we have a step pyramid. Now, the pyramids have some similarities. They're both the same height. Turns out they're both 8 inches tall. I think you can see it like that. Same height, and the bases are the same size. Each of these two pyramids has a base that's 8 inches by 8 inches. Anyway, let's look at the different layers of the step pyramid here. The top layer is 1 inch by 1 inch by 1 inch, so it's 1 cubic inch. The next layer is 2 inches by 2 inches by 1 inch, so that's 4 cubic inches. And on down to the bottom, where the bottom layer here is going to be 1 inch tall by 8 inches by 8 inches, or 64 cubic inches. So let's review the volumes of all 8 layers. The top layer is 1 by 1 by 1, or 1 cubic inch. The next lower layer is 2 by 2, or 4 cubic inches. Then 3 by 3 is 9, 4 times 4 is 16, 5 by 5 is 25, 6 times 6 is 36, 7 times 7 is 49, and, as we said before, 8 times 8 is 64 cubic inches. So when you add up the volumes of all 8 layers, you get 204 cubic inches. Now, the pyramid is surrounded by a cube which has the dimensions of 8 inches by 8 inches by 8 inches, or 512 cubic inches. So the ratio of the volume of the step pyramid to the volume of the surrounding cube equals 204 divided by 512, or 0.3984. But wait a minute, 0.3984 is quite a bit bigger than 1/3, which equals 0.3333. What's going on? Here's what's going on. When you line up the pyramids, parts of the step pyramid are peeking out behind the smooth pyramid. Okay, here's a graphic depiction of what we just saw with a paper model. Here we have a smooth pyramid, and behind it is a step pyramid with the same base and the same height and 8 layers. You can see quite a bit of the step pyramid is peeking up from behind the smooth pyramid. But let's say we didn't have 8 layers. Let's say we had 16. It would look like this. And less of the step pyramid would be peeking out. Or if we had 32 layers, it would be like this. Or if we had 64 layers, it would be like this, with very, very little of the step pyramid peeking out from behind. Now, as it turns out, the more layers we have, the closer we get to 1/3 when we compare the volume of the step pyramid to the volume of the corresponding cube. Now here's a graph that shows the relationship of the number of layers in the pyramid to the ratio of the pyramid's volume to the volume of the surrounding cube. When we go from left to right, the number of layers is increasing from 0 to 32. And when we go up, the ratio of volumes is changing from 0.3 to 0.5. The dotted line shows where we've got a ratio of volumes of precisely 1/3. Now, with our model pyramid, we had 8 layers and the ratio of volumes was just a little bit less than 0.40. But as the number of layers gets bigger and bigger, the ratio of volumes gets closer and closer to 1/3. Okay, let's use the whiteboard now to delve a little more deeply into this concept of the excess above 1/3 that we just calculated. According to math textbooks, when you take the sum of the squares of the first n positive integers, you get 1/3 times n cubed plus 1/2 times n squared plus 1/6 times n. Now we're not going to try to prove this formula right now at least, and we're not going to try to derive it, which would be even tougher, but what we will try to do is at least check whether it's true in the special case where n equals 8, because we've already checked that out the hard way, doing the calculations number by number. According to this formula, the sum of the squares of the first 8 positive integers should equal 8 cubed divided by 3 plus 8 squared divided by 2 plus 8 divided by 6. Doing the arithmetic, the next step would give us 512 divided by 3 plus 64 divided by 2 plus 8 divided by 6. Putting this together, finding the lowest common denominator, and then doing the final division, the suggestion is that the sum of the squares of the first 8 positive integers is equal to 512. Is that what we calculated before?
Yep, that's what we figured out.
So far, so good. Now, earlier we calculated the ratio, the volume of a step pyramid with 8 steps by the volume of the corresponding cube that you could build around the step pyramid. When we did that, the volume of the 8 steps together was 212, and the volume of the surrounding cube was equal to 8 cubed, or 512. But now we want to look at the general case, not the special case where the number of steps is equal to 8. So rather than dividing by 8 cubed, we'll be dividing by n cubed. So if we have a cube with dimensions of n by n by n, and inside this cube we build a step pyramid where the height of each step is equal to 1, then the combined volume of the steps of the pyramid will be equal to 1/3 n cubed plus 1/2 n squared plus 1/6 n. But if we want to get the ratio of the volume of the step pyramid to the volume of the surrounding cube, we've got to divide by the volume of the surrounding cube, which is equal to n cubed. Simplifying this, the ratio of volumes will equal 1/3 plus 1 over 2n plus 1 over 6 n squared. Again, This is the ratio of volumes. Now, if the number of steps in the step pyramid is equal to 8, let's say, then the value of 1 over 2n plus 1 over 6n squared is going to be a non-trivial number. But as n gets closer and closer to infinity, then the value of 1 over 2n approaches 0, and the volume of 1 over 6n squared also approaches 0. So as the number of steps in the pyramid approaches infinity, the ratio of volumes approaches precisely 1/3, which is what we've been trying to demonstrate.
Hey, didn't we prove that 10 minutes ago?
Sure, but we didn't want to miss out on those 10 minutes of fun. And besides, what we're really doing with this discussion of limits, with this discussion of how one value gets closer and closer to 1/3 when another related value gets closer and closer to infinity, is laying the groundwork for the adventure of calculus. Oops. Even when you think lofty, abstract thoughts, you should be careful about the details. Anyway, here's the basic idea of this whole video. If you take a pyramid and you slice it up into billions upon billions of equally spaced cross-sections, then you take the average area of all those cross-sections. What you'll get will be 1/3 the area of the base.
Did God have a choice when he made the universe that way?
That's a great question. But alternate universes are beyond the scope of this video.